right, so now we're going to talk about division with complex numbers. And of course, before we can talk about division, we need to talk about multiplication. So when you go to multiply two complex numbers, you can follow the rules of FOIL. So first outer, inner last. So when we look at 5 minus 3i and multiply it to 2 plus 6i, multiply the first terms, 5 times 2, multiply the outer terms, 5 times 6i, multiply the inner terms, negative 3i times 2, and then the outer terms, negative 3i and 6i. And this is where the I and the I give you the I squared. You got to remember to turn that into negative 1 when you simplify. So you can combine these together easily, but negative 18i squared is the same as positive 18. And now we can combine these together to get 28 plus 4i. So when you multiply two complex numbers together, you should get another complex number. Okay? So what is a complex conjugate? Well, we've talked about conjugates before when we dealt with radicals, but a complex conjugate is now dealing with complex numbers, obviously. So really the difference between a complex conjugate is one has a plus bi and the other is a minus bi, and they usually come in pairs. And just like we did before, if we multiply these out, look at, go ahead and FOIL them, but you can think of these as the difference of two squares. It's just not the difference anymore, it's the sum, because you have that I times I, that I squared, that changes the minus into a plus. So this is really interesting. This allows us to now factor the sum of squares. It just means that when you factor them, you end up getting imaginary numbers or complex numbers instead of real numbers. So try it. Factor the x squared plus 3. So putting it into this form, a is going to be x, and the b is the square root of 3, and then we'll have an I for both of them. So just kind of keep your mind open to that, and don't automatically think, oh, this can't be factored anymore. We're done, because you're not. You can factor using complex conjugates. Okay, now, what we're going to be doing with the complex conjugate as well is to be able to rationalize the denominator. So this denominator, 6 plus 7i, if I just multiply the top and bottom by 7i, that's not going to do anything to eliminate the imaginary number down there. So what I do have to do is multiply by the complex conjugate, 6 minus 7i. On the top, you're going to multiply this out, just FOIL like you normally would. On the bottom, since these are complex conjugates of each other, you could either FOIL it out and simplify, or you can remember our rule that it's the sum of squares. So on the top, when you FOIL this out, you get this big whole expression. On the bottom, sum of squares, it would be 6 squared plus 7 squared, which is 36 plus 49. Remember, this I squared is a negative, so this becomes negative 35 that you're adding to a positive 12 to get negative 23, and then you combine these together. And that's it. That's as far as you can go. But now it's been rationalized. All right, and so just the last example here, remembering about factoring, x to the fourth minus y to the fourth. This is the difference of two squares. And if we went through and factored that, this is what we would get. And then we could even factor further by saying x squared minus y squared. That's a difference of squares again. And typically in the past, we would stop. So if we were back in our polynomial factoring chapter, this would be the end. This would be the final answer. But now that we have complex numbers, this can be factored even more into the complex conjugates of x minus yi and x plus yi. So that would be the complete factored form over the set of complex numbers. All right, there we go. We are done for today.